Section 16.6 Nuclear Fission and Fusion. During the 1930s, scientists bombarding uranium-235 with neutrons discovered that the U-235 nucleus splits into two smaller nuclei and produces a great amount of energy. This was the discovery of nuclear fission. The energy generated by splitting the atom was called atomic energy. A typical equation for nuclear fission is a neutron plus uranium-235 becomes uranium-236, which breaks into krypton-91 plus barium-142 plus 3 neutrons plus energy. If we could determine the mass of the products of krypton, barium, and 3 neutrons with great accuracy, we would find that their total mass is slightly less than the mass of the starting materials. The missing mass has been converted into enormous amounts of energy, consistent with the famous equation derived by Albert Einstein, E equals mc squared, where E is energy released, m is the mass lost, and c is the speed of light. Even though the mass loss is very small, when it's multiplied by the speed of light squared, the result is a large value for the energy released. The fission of 1 gram of uranium produces as much energy as the burning of 3 tons of coal. Chain reaction. Fission begins when a neutron collides with the nucleus of an uranium atom. The resulting nucleus is unstable and splits into smaller nuclei. This fission also releases several neutrons and large amounts of gamma radiation and energy. The neutrons emitted have high energies and bombard other uranium-235 nuclei. In a chain reaction, there's a rapid increase in the number of high-energy neutrons available to react with more uranium. To sustain a nuclear chain reaction, sufficient quantities of uranium-235 must be brought together to provide a critical mass in which almost all neutrons immediately collide with more 235 uranium nuclei. So much heat and energy build up that an atomic explosion can occur. Figure 16.7. In a nuclear chain reaction, the fission of each uranium-235 atom produces 3 neutrons that cause the nuclear fission to be more and more uranium-235 atoms. Nuclear fusion. In fusion, 2 small nuclei combine to form a larger nucleus. Mass is lost and a tremendous amount of energy is released, even more than the energy released from a nuclear fission. However, fusion reaction requires a temperature of 1 × 10⁹ Celsius to overcome the repulsion between the hydrogen nuclei and cause them to undergo fusion. Fusion reactions occur continuously in the sun and other stars, providing it with heat and light. The huge amounts of energy produced by the sun come from the fusion of 6 × 10⁻11 kilograms of hydrogen every second. In a fusion reaction, isotopes of hydrogen combine to form helium and large amounts of energy. In a fusion reactor, high temperatures are needed to combine hydrogen atoms. Scientists expect less radioactive waste with shorter half-lives from fusion reactors. However, fusion is still in the experimental stage because of the extremely high temperatures needed to have difficult to reach and even more difficult to maintain. Research groups around the world are attempting to develop the technology needed to make the harnessing of fusion reaction and energy reality for our lifetime.